Ferromagnetism. Ferromagnetic order. A ferromagnet is a specimen or substance which has spontaneous magnetic moment or spontaneous magnetization even in absence of external field. Even if there is no external field, the magnetic moments get oriented in certain direction to give rise to a net magnetization. In ferromagnetic material, magnetic moments and electron spins are arranged in a regular manner. Order of the moments, magnetic moments need not be a simple ferromagnet as shown in the figure below. Figure shows a simple ferromagnet in which magnetic moments are aligned parallel to each other. This specimen will have a net magnetization. Here, the magnetic moments in this figure, magnetic moments are anti-parallel to each other. Nearest neighbors are anti-parallel to each other, but their magnitudes are different, hence it possesses a spontaneous magnetization and is a ferromagnet. This is the figure of a centered antiferromagnet. The magnetic moments are anti-parallel, but this also possesses a magnetization, spontaneous magnetization. The third figure shows a helical spin array. The magnetic moments are neighboring magnetic moments are arranged in a helical fashion, and this also possesses a spontaneous magnetization, hence it is a ferromagnet. The last figure shows a simple antiferromagnet in which the neighboring and magnetic moments are anti-parallel and their magnitudes are equal. Hence they get cancelled and the net magnetization is zero. Curie point and exchange integral. Let us consider a paramagnet in which there are permanent magnetic moments but they are not oriented, thus magnetization is zero. Consider a paramagnet with a concentration of n ions of spin s. Let there be certain interaction, internal interaction between these spins. These spins are tiny magnets. Therefore, there is interaction between the spins that will tend to line up these magnetic moments parallel to each other, which will be equivalent to a ferromagnet. Let such an interaction be called as exchange field, the field due to neighboring magnetic moments which will align a magnetic moment in certain direction is called exchange field. This exchange field orient the magnetic moments and orienting effect is opposed by thermal agitation and at a higher temperature, a particular higher temperature, the order will be destroyed. Exchange field is equivalent to a magnetic field BE of a magnitude 10 raised to 7 Gauss or 10 raised to 3 Tesla. This is due to neighboring magnetic moments. Let's assume that BE, exchange field, is proportional to magnetization M. Magnetization is magnetic moment per unit volume in a thermal equilibrium at temperature T. If domains are present in the material, magnetization refers to magnetization within the domain. And due to this magnetization, the field is produced called exchange field. Therefore, B is proportional to M. In mean field approximation, we assume that magnetic moment experience, each magnetic moment in the material experience the exchange field which is proportional to magnetization of the domain. That is BE equal to lambda into m, where lambda is a constant called mean field constant. Thus, each moment sees an average magnetization produced by all other spins. Curie temperature Tc. It is the temperature above which spontaneous magnetization vanishes and the ferromagnet becomes paramagnet. Thus, Tc separates a disordered paramagnetic phase at a T greater than Tc and ordered ferromagnetic phase at T less than Tc. In paramagnetic phase, applied field causes magnetization. If we apply an external field BA, this will cause a magnetization in the paramagnetic material. And this magnetization can cause or generate this exchange field BE. If chi P denotes paramagnetic susceptibility, then we can write magnetization in paramagnetic susceptibility is equal to chi P into magnetization in paramagnet is equal to chi P into BA plus BE. So BA is applied field and BE is exchange field produced by the magnetization in the domain. The paramagnetic susceptibility chi P obeys Curie's law. We formulated in quantum theory of paramagnetism. Chi P equal to C by T, where C is Curie's constant and its value was also found Np square mu b square by 3 kb, where P is equivalent number of magneton. Let us substitute equation 1, that is BE equal to lambda m in equation 2, that is m equal to, here we can substitute lambda m, then we get this equation m equal to chi p BA plus chi p lambda m. Now let us bring the terms of m to one side, that is m into 1 minus chi p lambda equal to chi p into BA. In this case, susceptibility is ferromagnetic susceptibility. We can write as m by applied field BA. That will give, from the equation, m by BA gives chi p divided by this term 1 minus chi p into lambda. Now substitute paramagnetic susceptibility chi p equal to C by T in equation number 4. We get chi as C by T minus C lambda. This is equation number 5. The C lambda we can substitute as Tc, particular temperature called Curie temperature, and equation 6 is called Curie-Weiss law. When T becomes Tc, denominator becomes 0 and chi becomes infinite. That means there is spontaneous magnetization even in absence of field, since chi is equal to m by BA. Even though denominator is 0, since C by T minus Tc, denominator becomes 0 at T equal to Tc, chi becomes infinite. That means there is magnetization even in absence of field. The value of C from quantum theory of paramagnetism, Curie constant, is Np square mu b square by 3 kb, where P is effective number of magneton, G into j plus 1 the whole raised to half. Therefore, this is the equation for Curie constant. From this, we can determine mean free constant, mean field constant, lambda as T by Tc from this equation. Lambda equal to lambda c equal to Tc. We substituted lambda c as Tc. Therefore, lambda equal to Tc by c. From the equation, we can substitute value of c. Therefore, lambda becomes 3 kb Tc by Ng square j into j plus 1 mu b square. Now, exchange field gives approximate representation of exchange interaction. From quantum mechanical, uh, we can show that quantum mechanically the interaction energy of two atoms having spin Si and Sj contains a term like this: the potential energy, interaction potential energy between two magnetic moments equal to minus 2j Si dot Sj, where Si and Sj are spin angular momentum due to two atoms I and J. Here J is called the exchange integral term and equation 8 is called Heisenberg model. The relation between the exchange integral and Tc can be obtained as this equation number 9, J equal to 3kb Tc by 2z into S plus 1. Here Z is the number of neighbors of an atom.